where we left off last week on this topic of quote unquote system hacking. Really, we were diving into a little bit of the alphabet soup of ways we can systematically talk about vulnerabilities and corresponding exploits. And I think it starts a little slow because it's a little bit abstract that you have CVEs and NVDs and CVSSs and CWEs. I think we're probably better served by just kind of looking at quote unquote real example to understand in practice what does this all mean. Because first off, I do think it's interesting. It's always interesting to look at vulnerabilities and to look at corresponding proof of concept exploits. And also what makes it interesting is it's an attempt to provide this systematic and quantifiable way of thinking about security. But I believe when you look at it, even the couple of examples we're talking about today, I think you'll come away with the impression that, well, it's not that quantifiable. We can provide a score, we can provide a number. There's a lot of ambiguity just fundamental to this field, which I think it makes it kind of interesting as an engineering sub-discipline here. So where we left off last week, we were talking about these CWEs, and they are related. I don't want to get too much into the CWE. A CVE is based on one or multiple CWEs, but that's really the truth of it, right? You have some sort of software or hardware security weakness. Another way to think about that is somebody implemented something not as well as potentially they could have. They are almost always due to either insecure system design, insecure software, or I'll bring up a couple examples of insecure hardware design. There are a lot of different CWEs, and then they're broken into different categories. And where we left off on Thursday is just an example of the use after free one. And we talked about how, yes, I would never write a piece of code that does this because it's such an obvious bug in my code, but it can lead to those type of outcomes. But in practice with complex code bases, even acknowledging the fact that this is something you don't want to have in your code, even there being a whole suite of tools that basically check for this kind of problem in your code that can automate that detection for you, it still persists. It still is on the top 10 known exploited vulnerabilities, the CWE top 10 list. The version I have on this slide is the 2023 version. If you go to the main CWE website, you will see the most recent 2025 version. I didn't update the slide. I could have. It's still roughly the same. There's kind of a reshuffling of some of those. The one that we noted last week is now the listed as number one top weakness, is something we also briefly looked at, which was the more formally listed as improper neutralization of special elements used in an OS command, otherwise known as OS command injection. And the idea behind that one is you have some sort of tool flow or process or ways of interacting with a piece of software that does ultimately correspond to crafting a command to be sent to a shell. That is the intention of the piece of software. We do that because, as we've seen, the shell is very powerful. We can pipe 17 commands together and do some pretty complicated things without really having to write a line of code per se. And so tools do that a bit. Do that maybe more now than even 5-10 years ago. And if you are not careful and you don't carefully check the inputs that are being passed to those programs, those command queues that are put together, you can accidentally have this vulnerability or inadvertently have this vulnerability that can lead to OS command injection. So I show that example there, but in terms of at a very high level, let's look at what that is actually in practice. So this is just one example of a command injection vulnerability. This was from, I pulled this up just from the same CWE link that previous page was, CVE 2025, 44, 844, what have you. This is a particular Wi-Fi router and a whole family of Wi-Fi routers that has a command injection vulnerability. So let's attempt to demystify what is actually happening here as best as we can. So there's a high-level description, and again, this is the NVD website at NIST. There's a high-level description that has a command injection vulnerability in a particular set upgrade firmware function via the file name parameter, And this vulnerability allows attackers to execute arbitrary commands via a crafted request. Corresponding to that CVE, which is due to that particular CWE, tends to be some sort of proof of concept. Now, these things don't all appear at once. There could be a disclosure. Someone says, hey, I found this problem in this particular software or other product. Here's what I'm able to do. Then there is some sort of negotiation in which the NVD determines here is the CVE listing, here's the number we're assigning to this, and then after some point, here's our analysis of it and a determination of perhaps how severe that vulnerability is, and usually then only after some reasonable period of time in which potentially the software developer or manufacturer is able to remediate the issue, then there's some sort of public disclosure of what the actual nature of the vulnerability is. It's not necessarily a race to kind of get that information out there publicly first, but there's a period of time in which it's discovered, it's at least an alerting stage of the manufacturer or developer, and then eventually after some reasonable period of time, which is not really formally defined, some sort of public disclosure of what the actual vulnerability is. So again, the weakness here, improper neutralization, okay, OS command injection, something that by design is meant to basically be putting together some sort of command line argument or set of arguments, and it's not sufficiently carefully checking what user input is going to be for it. I like this example because it's relatively recent. It's the first one listed on that page. It's also sort of trivial. Again, another example where we had the use after free as a proof of concept common weakness, and you would hopefully say when you looked at that code, oh, I would never do that. That would never happen to me as a developer. Well, this one is a real-world actual example of this particular CWE and what that can look like in practice. So this is the firmware for that particular, this is a power over Ethernet adapter, but sure, that has a web accessible call to upgrade the firmware. And as part of that, it's going to request via a parsing of an HTTP request, a parameter called file name. And it's going to attempt to remove that original file name before it then updates the new firmware. So there's some ellipses here where it's not showing everything that's happening here. But again, that is the example. That is a command line argument. Sprintf, as printf, takes that print string and store it to a string called v32. And then this is some sort of shell. Run the command is what that next line is doing. rm-f, so remove file of that file name. And that has something to do with processing the outputs so that we're not seeing a bunch of outputs from that command, given what that input file name parameter was. So that is the actual crafting of the OS command here. So far, so good within a reasonable way one could write it. Maybe your code would look different. It's taking a user input, it's crafting like a bash style string to then actually execute on the device itself. The proof of concept now is that we actually are doing a post request to the actual code that's going to execute that setup firmware function, and we're going to pass it the parameter file name, and that file name is actually going to be something like pwd, print the working directory. So instead of actually just removing something, it's going to remove something, and because of how we're actually crafting that, where's the actual injection? What part of this file name turns that into an injection? Do we know by looking at it? It might be a little small on your screen. The whole thing is an injection. What is the thing the attacker included there for the proof of concept? The semicolon, right? So the semicolon is saying, well, I'm supposed to be passing a file name, but I'm really just passing a string. If that string includes a semicolon, well, what is it actually going to do? Because that line of code is written by a trusting person, I guess, or someone who didn't really think of the security implications of that line of code, it's going to do the rm-rf command, and then that's the end of the command, and the next command is going to be, again, for this proof of concept, print the working directory, leak some information, provide some information back out. That command then, if you can execute that command, you're limited by just whatever other user level permissions are on that device. You now have shell, you have whatever you potentially want on that particular device. That's one example here. I think I have, well, we'll go to it in a second. Those vulnerabilities, those CVEs, are then at some point assigned a CVSS, a common vulnerability scoring system. It's an attempt to provide some sort of standardized ways of saying how severe a vulnerability is. An attempt for you as someone who's maybe managing an IT infrastructure to say, this CVE has been publicized, it has a number at least associated with it. That gives me some sort of quick heuristic as to how much I should care about that particular vulnerability. At the end of the day, that's a very difficult thing to manage properly. And there would be whole teams in a large enough organization whose primary responsibility would be for understanding the sort of kind of steady fire hose of CVE releases out there of the software and products that you use, and determining really on a case-by-case basis what the action plan needs to be as an organization. Sometimes it's as simple as there's a CVE, it gets publicized the same day as a patch is released, or sometimes after when the patch is released. Just keep up to date with patches and you're fine. Other times there may or may not be a manufacturer or software developer released patch, and then as a team you have to really determine what is our next course of action. Do we discontinue the use of this software or this particular product? Do we attempt to remediate ourselves with regards to custom fixes? But at the end of the day, security is not binary. I think that's probably one takeaway from this entire lesson. It does provide what is effectively a spreadsheet. It's not even a very big, I say a big equation spreadsheet. It's just a small equation / spreadsheet, but it could also lack pretty important context. So that's my joke there. If this CVE is only a 6.4, I don't have to worry about it. Does anyone know who that is? Okay. I'll put that on the quiz for not this upcoming week. There's different severity classes. Let's look again at this proof of concept and this particular CVE. So CVE on that particular PoE device, what would the severity score be for it? And when I say it is a spreadsheet or a web app or just an equation, that is all it is. There is effectively a negotiation. The discoverer of the vulnerability has their own opinion. The manufacturer of the device or software would also have their own perspective and opinion. And then ultimately the NVD, in this case it's NIST, has to make some determination as to the vulnerability score for it. And that can actually also change over time, but at least in that initial vulnerability score. If we go back to the listing for this one, it's listed as a 6.5. So it's only medium. I can go back to sleep here. Or not. Let's look at how that probably came into being here. This is the spreadsheet view or the web app view. There's different versions of CVSS. It's not that important. They're extremely similar. So this is 3.1. It had a listing for CVSS 3.1. You can look at 4.0. It's asking extremely similar questions. For the vulnerability, you're basically asking questions, and there's a guide. You don't have to go blindly into answering these questions as to how this vulnerability would actually have a security impact and how heavy that impact would be. And there's a little guide here just in looking at it. Start off, what is the attack vector? Meaning, how does one actually trigger an attack given this vulnerability? So again, I'm asking specifically about this one. We have a web interface for this device. We pass it kind of a malformed OS command. We get arbitrary code execution on the device. Is the attack vector, do I have to be physically present? Do I have to be kind of local, sort of logged in, nearby? Or can I do it over the network? What would we say? We're going to give our own CVSS score for this. Can I do this attack over the network? You're nodding. It's a super confident nod. Yes, yeah, you can do this over the network. That's all we're showing, right? In this vulnerability, and I may just have to keep tabbing back and forth, I guess you're looking at sort of the raw HTTP trace. We're just sending an HTTP request. We are remotely doing this over the network. Anyone who has access to the device over the network can launch this attack. attack complexity. And there's, again, a little bit of helper text there, and there's a whole guide for it. But now we're starting to talk about why it's not that clear cut, despite this attempt to quantify things. Is the attack complexity low or high? Well, I don't know. Is it low or high? What do you guys think? We'll take your vote. Sure. I feel like if that's not low, I don't know what low is, right? You trip over the cable and you trigger. I don't know what would be lower than this if this is low. Now, discovering it still requires, ingenuity and careful inspection and understanding systems. And, it's not a trivial thing, but once it's discovered, the actual complexity of carrying out the attack to me seems quite low. So those are two separate considerations. Privileges required. None, low, or high for this one. Does someone require privileges? Meaning you have to already have a valid account on this device, and then you're kind of escalating your privileges to do this? I would say no. These are all the defaults, but so far the defaults are working for it. User interaction. Does the user have to kind of be like tricked? Someone here, the user is someone other than the attacker. Does the user have to kind of tricked into doing something like clicking a link to be able to trigger this attack? I would say that is also a no here. So far we don't have to click anything, and so far though our CVSS score is 0. So that's how the attack actually is triggered, but doesn't really tell us anything about the severity yet, which is kind of interesting, right? Because I would argue we have to change some of these things here, that if someone requires physical access versus network access, that should change the severity. We'll see once we talk about the confidentiality, integrity, and availability, it will also trigger it here. But so we have the scope of the attack, and I'll just quickly read off. Does a successful attack impact the component other than the vulnerable component? In this case, other than the vulnerable component, I think it's no, right? We're looking at this particular device, and we're trying to get additional access via this particular device. So no, it's kind of unchanged. It's kind of local scope to it. Okay, now we know our CIA triad at least a little bit. Confidentiality, right? What kind of information resources get modified or get impacted by a successful vulnerability here? It can't be none here, right? So when I'm able to run arbitrary commands on that particular device that was not intended for an attacker to be able to do, it's at the very least low. I'd have to look into the guide to say what is the difference between low and high here. The help text says high is a total loss of confidentiality versus a partial loss of confidentiality. Here's where we start to see that this can be kind of a negotiation, right? Why is this not a total loss of confidentiality? There could still be some secrets that the particular web client is running as that would not have access to other things potentially on that device. So there may be some limit. That becomes a negotiation more than a clear matter of fact thing. We'll list that as low. It's hard to have total confidence in those things, but low impact to confidentiality. Integrity, am I going to be able to modify the veracity of information here? And again, none cannot be the case. Total versus just partial sounds like that is also a low scenario here. We're kind of just considering it. And then availability. Are we basically going to be able to take this component down via this approach? Are we going to impact services? Now, if you were to ask me for this, I would imagine it's possible. This proof of concept doesn't provide enough evidence that that is the case or not the case. Can I shut the whole thing down? Can I brick it? Can I do that kind of thing? I would think the answer is at least low, and we can click that. When we click low there, well, what has happened? Our CVSS score has gone from a 6.5 to a 7.3. It has gone from a medium concern to a high concern, and I hopefully from that just little toggle you are starting to get my point, which is, of course, security is not binary. I can go back to my NAP if it's a 6.5 versus a 7.3. That's nonsense, right? The vulnerability is exactly the same. The vulnerability didn't change, right? It's still the same command interjection capable via that particular web accessible function. What has just changed is our quantifying how severe we believe it to be based on this spreadsheet, based on this sort of high-level rubric. If we were to go back to the CVE page for it, it is listed as a 6.5. It can be kind of hard to read. We have a 6.5 medium score here, and then this vector, it does actually kind of provide it for you. You're provided with this string, this kind of text string, which kind of looks like nonsense, but that's all that text string is. For those base components of the CVSS score, those are the toggles, those are the spreadsheet entries, those are the input variables to your algorithm. It is literally just saying attack vector, network, attack complexity, low, privileges required none. It is just a direct kind of ASCII text encoding of those same exact things that we have on this page. Questions about CVSS or how this generally works? One takeaway is that these things are a process, not a kind of capital T truth that we can always kind of refer to. Another takeaway is, medium may or may not mean medium. High may or may not mean high for you as well in terms of the severity, the potential impact. Just receiving a number saying, well, today we got a 6.3, today we got a 6.5 that affects a piece of software we are using, doesn't absolve you of the responsibility to investigate, to understand, to figure out a remediation path. The converse is also true, right? Just because something is a 9.8, whatever, may or may not mean that much for you here. It would not be hard to find a 9.8 example here. This is OS command injection. There's just a listing of recent ones somewhere on this page of examples of command injections. Virtual, okay, here we go. Here's relevant. let's click it. Shell command deny list bypass in one of those auto GPT agent softwares. A vulnerability in this piece of software allows an attacker to bypass the shell command's deny list settings. The issue arises when the deny list is configured to block specific commands. But an attacker can circumvent this restriction by just executing the commands with a modified path. So that is definitely another software bug. You're telling this particular piece of software, do not execute this particular command, take user inputs or restrictions of what commands are available, but then limit which ones are possible. But as we know, there's a lot of different ways one can encode a command. In this case, instead of just running the command from the path, it's run the command with a hard-coded path, and you can go up, you can go down directories, you can have symbolic links. There's lots of ways one can kind of hide or conflate the path associated with it. What's different also then about this one, it's listed as critical. The CVSS score for this one looks similar at first blush. This version of the CVE website does not provide the little helpful text here. Let's see what we got here. That link opened up, that's the same link. Here's the Auto GPT library where you specify, this is a proof of concept. This is someone showing the proof of concept like before. Here's a list of commands that you're not allowed to run. Again, just like the pwd command on the prior example, just meant to show a somewhat innocuous example of, pwd itself isn't that big of a deal. Who am I is just printing out the current user logged in on the machine. You've done that a couple times in lab. Just proof of concept, something kind of safe and innocuous, which is say, don't run these commands. But now you can tell it to instead execute this command, which should not be allowed, is allowed, and then your AI agent, which you're attempting to kind of manually sandbox here, which is probably never going to truly work if in this approach, at least for that particular attempt to restrict its functionality, is in fact not going to work. Now, so for Auto GPT, the idea is you're passing tasks in a programmatic way that then get passed off to a virtual environment to execute and run your code for you. And there's a lot of competing open source and proprietary projects in that space. I guess that is a vulnerability. If there is this particular feature, which is, here is deny list of commands, I never want my agent to ever run for me on this environment, and you have a workaround that does allow it to run those commands, that is certainly a vulnerability. Now, why is it such a large number here? I have the wrong link open. Because at first blush, it's not that different to me. It is different. The other one's just such a clear, sort of programming flaw that they don't escape the bash commands that are being sent to it. And there's ways to sanitize that input. This one is also very similar. It's someone who's a user of their own software, their own system. They're interacting with it via sort of a network request. So that aspect of it should be exactly the same. Let's go look at the actual scoring system. Confidentiality loss. The only way you get to 9.8 is if you claim that for basically the same exact attack vector, all three of the CIA is now high, is now total versus partial. So when we talk about these scores, is this vulnerability worse than the other one? I don't know. That's my unsatisfying answer, right? Depends on your use case. They're actually quite similar in terms of the weakness that they're both exploiting. They're both a piece of hardware or a piece of software that you yourself are configuring and working with. In this case, I would call this just a fundamental flaw in the product itself versus something that itself is a vulnerability, that it's not going to be a piece of software that you're going to really be able to limit what kind of commands could be run if you are trying to trick it into running those commands. That's my thought of it. So one has a 9.8, the other has a 6.5. To me, they're both kind of equally important, but it also then ultimately depends on your use case as well. And finally, these CWEs are also hardware. The primary concern or consideration is software vulnerabilities. And I think a lot of times classes like this one focus entirely on the software side of things, but it also is an attempt to encapsulate hardware vulnerabilities as well. And I know some of you have a hardware background or are developing a hardware background. If you're in electrical engineering or if you're in computer engineering, that's all we mean by hardware. So digital design or analog design. And I think oftentimes we do focus on software vulnerabilities and don't think of the fact that hardware has a similar nature of vulnerabilities. They tend to be more subtle. They tend to be much harder to fix after the fact. If you've created a piece of hardware and you've released this product, you can't necessarily patch your hardware unless there's some firmware kind of approach. But there are also CWEs that correspond to hardware weaknesses as well. This starts to sound a little bit more double E, or certainly at least computer engineering, where improper protection against voltage and clock glitches. Things like, I have this secure device and it's got some secret key, and it turns out that if I just undervolt it or try to mess the clocking circuitry associated with it, I can cause it to leak that information. Some of these are pretty subtle. So improper protection of physical side channels, the kind of thing, if you are interested in, you do get an opportunity to learn more about at Iowa State, not until that 4,000 and 5,000 level. The class that would cover physical side channels is CPRE 5380. As undergraduates, you're allowed to take that. You just have to probably get to your senior year. Looking at the fact that we designed this digital hardware to do secure things like running cryptographic algorithms of the kind we talk a little bit about. You'll learn more about in 3310. If we are not super careful with how we implement these things, even if logically all the ones and zeros are always exactly correct, we can wind up inadvertently leaking information to a fairly advanced attacker. And when we talk about a hardware vulnerability, they tend to be of this nature, where the logic is probably still correct. So it's not like the use after free bug or not sanitizing your command line arguments to a shell type of bug, but instead it's our implementation is logically correct, but we didn't think about the double E side of things with our implementation. And a lot of those are grouped together into this broad category called side channels, or in this case, physical side channels. I'm guessing you will not see CVEs for these side channels. There's a couple. Google Titan security key. I was trying to look at an example. So here's an example now. Here's some Verilog. I bet you weren't expecting Verilog in this course. This will probably be the last Verilog you have to see in this particular course. Hardware design language, for those of you who didn't take digital logic course. We're building a piece of hardware to implement some kind of math or some kind of processing operation. Usually when we're talking about side channels, we're talking about hardware implementation of cryptographic primitives. This example is a modular exponentiation module for RSA, public key cryptography. The idea being that we have something that is probably logically completely correct. Someone know enough Verilog? What is that line of code doing, or that highlighted block of code doing? Just those two lines. 2810 was a while back. There was some debate whether there's any Verilog in 2810. There's supposed to be a little bit. Just checking. No, it's a latch. Okay, that's fine. You don't need to know that. This is not a hardware design course. So if we have some sort of check on a value, if this value of this particular bit, which the assumption is it's storing an intermediate result of the cryptographic computation here, if that particular bit is equal to 1, that's kind of the default, then it says result reg here, but that would be a latch. Latch the value. Store the value for future processing. So it's some sort of latch instantiated in hardware. That seems like perfectly valid code, and I think logically it is. It's probably doing what it's intended to do. The issue, though, is that once you have code that triggers, and we're talking hardware code here, that triggers, or it could be low-level software as well, but that triggers based on secret information in the actual implementation itself. If only bit 0 of that register is high, then latch this particular result. That potentially leads to the so-called side channel. Because in theory, if I have this device, and it's the chip corresponding to those lines of Verilog code here, think like the FPGA-based platform you would have briefly used in CPRE 2810 for those who took that course. And I have some way of very accurately measuring either the timing associated with it or the power consumption associated with it. Then what can happen is, given an appropriately set configuration of input tests to that device, I may be able to measure that. When bit is 0, bit register of 0 is 0, I get this kind of power profile, and when it's 1, I get this slightly different power profile. And with very precise measurement and some sort of differential analysis that tends to happen, we actually wind up with ultimately what's a hardware weakness here, or a hardware vulnerability, that there's this secret information that's meant to stay on the chip, and we wind up kind of leaking it inadvertently. In this case, via just a slightly different power trace profile of the execution of this module. In other cases, timing is the thing that really can kill cryptographic implementations. If I have any kind of branches in my code that are dependent on some secret information, if key value is greater than 10, do this, otherwise do this. As soon as that's in your code, you at least in theory have that weakness, you at least in theory have that vulnerability. Being able to actually exploit that kind of thing requires some fairly low-level double E style knowledge, but it is feasible. There's been plenty of proof of concepts in practice that do show that. So I just wanted to show that CWEs, we think of it as being software vulnerability. It's also going to be hardware vulnerabilities as well. My bias is I kind of like talking about hardware design and hardware vulnerabilities. This class doesn't need to get into it all that much. Back to our alphabet soup, another way of systematically talking about exploits and vulnerabilities and how serious they can be. uses this classification known as CAPAC, the Common Attack Pattern Enumeration and Classification. This one, I think in some way is more useful than CVSS. It allows you to categorize attacks via the types of attacks, but more importantly, I think, because CWEs already kind of do that, it provides some way of kind of logically walking through the mechanisms of attack. If there is a particular weakness or something has already happened, I'm allowed to execute a somewhat arbitrary operating system command on this PoE device. This CAPAC classification allows us to kind of game plan, okay, consequently what? What could happen next? Whereas the CVSS score just says severe or moderate, or here's a numeric value to tell your boss to what extent they should be worried. The attack pattern enumeration and classification is what can happen next. And you can game plan through that. See if I have an example here. I have a lot of websites open. I'll get there. Okay, this is the same example that is being shown on that slide. There's hundreds of these things. So the idea is similar to what you're already doing in Lab 3. You have some sort of credentials on a particular access to an administrative share on a local machine or within a Windows domain. That seems bad, right? So an attacker has gained access to your machine, and it doesn't say necessarily how the attacker got access to those admin shares, but it does talk about ways that it can happen. So it is meant to be thought of as kind of a directed graph of getting from point A to point B to point C. Ultimately, there's some sort of vulnerability that allows some sort of initial access. How do we do this in Lab 3? We basically started with a dictionary-based password attack, right? If you haven't gotten there yet, it's fun. Given some hash type vulnerability, you can, if it's a common type of password, you can run these automated tools that check, is it some simple modification of some existing thing in a dictionary? So someone gets access to credentials. I think it opened up in a new tab here. They now have access to some administrative account, some administrative password. Now what can happen? So can follow is the previous node on the graph. How did we get to this point? Can proceed is what is the potential next node on the graph? Okay, someone was able to brute force the password. Someone has this administrative access. Now someone can execute local execution of code. That seems bad. At that point, I think things are probably game over. What are other things they can do? Can they pull data from system resources? It's a way to kind of break down sort of the attacker's perspective of, we have a CVE, we have this vulnerability that provides this type of access, answering the question of, well, so what? I have a number, so what? What does this 9.8 mean to me on my systems? What would happen if someone was able to demonstrate they have that level of access? CAPAC's a nice way to attempt to kind of provide a more systematic view of point A to point B to point C. And so I think it's useful for that, that purpose. Just like we were talking about common weaknesses in hardware, CAPAC also has supply chain as one of their domains of attack. Also things like social engineering. So it did show it briefly, but I kind of quickly skipped over it. One way that someone can get access to these stolen credentials is through password recovery exploitation, where sending a malicious or false email saying, hey, you need to click here to reset your password, and then that's how they get credentials. So it encompasses things we'll be talking about later in the semester regarding social engineering, but also talks about supply chain security, a topic we hardly would have talked about in a version of this class 10 years ago. I don't think the term supply chain would have even necessarily come up. And now it's really being seen as this kind of critical issue. Supply chain is thought of as this, manufacturing concept, and it is. How do we source the components that we then integrate together to build something more complicated? That's what we mean by supply chain. And it's a chain because you tend to be just one link in that chain, right? You are purchasing, motherboards, right, for the computers that you yourself are going to build and integrate. Those motherboards are purchased from a company. That company then sources particular RAM chips from a different company. Okay, that company then is making RAM chips. They're then sourcing, raw material or equipment from yet another company. So there's a supply chain for the product that we are making. Unless you're completely vertically integrated in a way that most modern electronics aren't, you are working your way alongside one or many supply chains to kind of build and integrate your product. That's been a very well understood concept, for a very long time here, since the Industrial Revolution, perhaps. Two things have really changed, though. One is this awareness that the supply chain itself is a potential vector for vulnerabilities. And here I'm talking about just the hardware supply chain. I provided those links. I was thinking, we take a few minutes in class and everyone kind of read a couple of those articles. I don't know if that's the best use of our time, so we won't do that. It would make a good discussion on Thursday, right? MQ Alpha on Thursday. We're going to take about 25 minutes and do that kind of, longer form quiz. Probably won't be really filling up to a grand lecture at that point. Maybe we'll jump into that article on Thursday, give you 5-10 minutes to read it, and then maybe discuss it as a group. That one's kind of fascinating. At least I find it interesting. This claim, as far as I can tell, completely unvalidated, uncertain claim that there was a proper supply chain infiltration on these servers that are used by all sorts of Fortune 500 companies here, in which a physical basic backdoor was inserted into those machines for remote access. So maybe we'll look at that article on Thursday. I think it's interesting enough because it's also pretty ambiguous. Did Supermicro's hardware supply chain really get exploited? Well, my answer is I don't know. It'd be nice to read a couple of those articles and get your take, your opinion as to what you're reading there. Maybe we'll do that on Thursday. So that's one interesting aspect. The supply chain, the physical hardware supply chain, is now seen as itself a big issue from I'm sourcing this product. Can I ever actually really trust the hardware that I'm purchasing? How do I know it's not just counterfeit or garbage in the first place? How do I know it doesn't itself have some hardware vulnerability? That itself is a relatively recent phenomenon and awareness raising there. There's political aspects of that as well, of course. The other thing that's changed that I think is becoming very relevant for you and more prevalent is the software supply chain, a term that didn't exist even maybe 10 years ago in any meaningful sense. The idea that the software we write or that we have chat write for us isn't really lines of code anymore, right? So much of our software development is just integration now. Integration of third-party libraries. Really, think about the last interesting piece of code that you wrote. And I'm not saying for a class assignment, which maybe you weren't allowed to do this, but for any project you worked on, what did you really do? You had some complex task, and you looked up what libraries, what packages, depending on your language, am I using to be able to accomplish this task? And there was 3 different libraries or 3 different packages from 3 different places, and you wrote code to kind of glue those together, to get them to work with each other, to convert data, whatever you had to do. And modern software development it's already there, but it has significantly trended in that direction. And oftentimes our choice used to be we would argue so much about which programming language is best for a particular task. You don't really get those arguments anymore. Now it's which package manager is best for our task, or which software ecosystem is best for our particular task. Who has the best standard libraries? Who has the best third-party ecosystem? But what has been seen, and here again I'm just talking about your Python ecosystem, your Arduino ecosystem, your Rust ecosystem, your Node.js ecosystem. These are all to some extent dependent on relatively open, but relatively third-party, free-for-all environments in which packages are maintained by people from all over the world with all sorts of different motivations and backgrounds. What has been seen is this understanding, and we could easily find 50 examples of that just via a quick search, that vulnerabilities can be inserted in that software supply chain as well. Intentionally, inadvertently, it's hard to say, but that is seen as sort of a critical, very difficult to solve problem as well. So CAPEC also then talks about that. Every piece of software that you don't control every line of code of is a potential vector for vulnerability. Just like with hardware, a much harder problem to solve, every device you use that you yourself didn't fabricate from the gates up is a potential vector. Now with our software, it's not so different. There's a significant supply chain for the software that we are using. Let's leave things here for today. We'll jump back here after our macro quiz on Thursday. I got a couple questions. People are worried about it. I don't think you have to be worried about Thursday. You can do the math in terms of the relative points and things like that. Just review lecture 1 through lecture 4. If after doing it you still don't feel great, review the corresponding. It's 3 chapters in each of those 2 books. Pick one of them, that would be fine. Just read. If you have any questions before Thursday, you can certainly post them on our Discord, and I'll be very happy to answer them, conceptual questions. Otherwise, just don't go in completely blind and just showing up, rolling out of bed on Thursday, and you'll be perfectly fine for Thursday. Okay? All right, thanks.